particular solution plus the general solution for the homogeneous relation. So it is similar to systems of linear equations. Okay. So you find a particular solution and then you add a solution where there is no term fn here. Okay. So now for this example in particular, our homogeneous solution is simple. So it is the constant sequence. And now we have a tool here. If fn is somehow of a form of a polynomial in n times an exponential term like this one, then we know that we have two cases here, but in either case we will know that the particular solution has some form. Okay, so this form is given here. So in the first case, if this s here, it may be 1 if there is no Turing term here. If n is not a root, then we will look for a particular solution of the form polynomial in n times s to the power n. Okay, and we know that the degree of this polynomial p here is smaller than or equal to t. Okay, and then we will use the method of identifying coefficients of polynomials to find the coefficients for Pn here. So let us look at this example to illustrate how we do it. Okay? So in this case, our Fn here has a simple form. Okay? So Fn, if we write it as the product of a polynomial in n times an exponential term, then here the polynomial is n itself. Okay? And since there is no other factor, the s here is actually 1. Okay? So we do not forget 1 to the power n here. Okay? So if there is nothing, we still need to add 1. And now we will verify if s equal 1 here is a solution, is a root of the characteristic equation. Okay? So our homogeneous relation is an is equal to an minus 1. So the characteristic equation is x minus 1 equal to 0. So effectively, s is a root to the characteristic equation of the homogeneous associated homogeneous relation. So we will look at the second case here. Okay. So it is the root of multiplicity n equal 1. Okay, so we will look for a solution of this form here. So I will write it. So we will look for a solution of the form n to the power 1. Okay? Because n here is equal to 1. Pn times 1 to the power n. Okay? And here, the degree of p is smaller than or equal to 1. So it is either a constant term or okay. So in general here we have this form. We look for a particular solution of this. We have n to the power multiplicity 1 here. Okay. So here we know that the polynomial has degree at most 1, so we can write it as p0 plus p1n. Okay? It's a polynomial in n. And here, if p1 is different from 0, is non-zero, then we have the polynomial of degree 1. And if p1 is 0, then we have a constant, which is the polynomial of degree 0. Okay? And we have s to the power n here. Okay? So, to summarize, we will look for a particular solution of this form here. Okay? And now we will plug this expression into our relation in order to find P0 and P1. Okay? So this is what we do. We replace an here in this relation with P0n plus P1n squared, and we replace an minus 1 with P0n minus 1 plus P1n minus 1 squared. So we have this, okay? And now the remark is that this must be true for every n, because it is the definition of our relation. But you know that this will be, if you simplify this, then you get an equation of degree at most 2 in n, okay? And you know that for a polynomial equation of degree 2, there are at most 2 roots, okay? But we know that this relation is true for every n. That means that this equation, this expression, after you simplify and move everything onto let's say the left hand side and put 0 on the right hand side, then for this equation to be true for every n, the left hand side must be 0. That means that all the coefficients must be 0. Okay. So here, if we simplify, we obtain this equation. Okay, 2p1 minus 1 times n plus p0 minus p1 must be 0. Okay. So this is true for every n. That means that both coefficients here must be 0. So if we solve 2p1 minus 1 equal to 0, we get p1 equal to 1/2. Okay? And the second coefficient gives us p0 is equal to p1, and then we find p0 equal to p1 equal to 1/2. And then we have finally found a particular solution of this form here. Okay? So you write it is n over 2 plus n squared over 2, and we get this. And now the final step is to use the initial condition. Okay? So now we have a general solution for the associated homogeneous relation. Okay? An is equal to C. We have a particular solution, and we know that the solution to this relation must be the sum of this particular solution and such a solution. So we have An is equal to n times n plus 1 divided by 2 plus C. And now, at this final step, we use the condition that I1 equal to 1. So we replace n with 1 here. We have 1 times 1 plus 1 divided by 2 plus C is equal to 1. And we solve it and obtain C equal to 0. Okay? So finally we can conclude that An is equal to this. You have already known it is a familiar formula. Okay? So of course you can use the similar technique to find, for example, a formula for the sum 1 plus 1 squared plus 2 squared plus 3 squared and so on. Okay? Or 1 cube plus 2 cube plus 3 cube and so on. Okay? So the calculation will be a little more complicated because the degree of the polynomial here will be will be higher. So we will have more coefficient to determine. But the principle is the same. You repeat the same steps, okay? And in the tutorial classes, you will do some exercises like this one, and you will see that after maybe 2 or 3 attempts, you will find that it is actually quite simple. Okay? So are there any questions? Okay? So, that was about linear recurrence relation. And now, today we will talk about a powerful tool in combinatorics. Okay? So, this is called, these tools are called generating function, and if you study advanced probability, then you will see that you will find similar concepts in probability. But now we will just look at a simple elementary introduction to generating functions and some applications in our counting problems or solving recurrence relation. Okay? So this lecture is divided into 3 parts. So the first part we will introduce the basics of generating function and formal power series. Okay? And then we will look at 2 particular applications of generating functions and power series. The first one is using generating function to count, and the second one is to use generating functions to solve recurrence relations. Okay? So the first part is quite technical compared to what we have already seen, but if you have done some, if you have had some courses in calculus, then you may find some similar notions and concepts. Okay? So now, what is generating functions? Okay? So, in our context, our generating function is usually associated to a sequence. Okay? So if we have a sequence, let's see a general sequence that we denote by an. This sequence is indexed from 0. Okay? Then we will associate this sequence with a formal power series, which is so. This series is a formal power series, and the coefficients, because the coefficients of this series are exactly the terms, the corresponding terms of the sequence. Okay, so here you have x power 0. So the coefficient is a0. Here x to the power 1. The coefficient is a1, and so on. Okay. So this is, we say that this power series is formal because this là một cái hình thức trong tiếng Việt. Okay? Formal because we don't associate a value. This is not a number. Okay? This is just an expression. These are symbols. Okay? There is no value. There are no values. So we don't talk about conversions or such concepts. Okay. So in calculus, whenever you write this, you need to verify that this is some converges. Okay. But in combinatorics, in our context, this is just a way to represent our sequence. Okay. So we write this infinite sum, and we write this, and we ignore the values, the conversions, and such. Okay. Okay. So those are the remarks, and of course, in this definition, we talk about general sequences. Where the number of terms is infinite, okay? But you can also apply this definition to finite sequences, because for finite sequence you can assume you can consider that all the further terms are zeros, okay? So actually a finite sequence is also represented not by a formal power series but by a polynomial, okay? Where the degree of the polynomial is the number of terms of our sequence. Okay, for example, if we have consider a sequence, O1 sequence, every term is equal to 1, then you have this series which is called the Maclaurin series, okay? And we will see that this series, in fact, we can simplify it. So the sum of x to the power n, where n goes from 0 to infinity, is you can find the closed form expression of the 1 over 1 minus x. Okay? So we admit that. So if, for example, the second sequence that we consider is the sequence where the term, the n term is n itself, then we get this series, and we can write it in with a compact notation using the summation notation here. Okay, and for this sequence, you may wonder why the index goes from 1 instead of 0. It is because d0 is 0, so we can ignore the term corresponding to the degree 0 here. Okay. So this, in fact, if you start with n equals 0 here, it's the same. It's the same sequence because it will add a 0 term which doesn't change the sum. Okay, so the third example is about a finite sequence. Okay, so as I said, for a finite sequence, you have instead of an infinite power series, you have a polynomial. Okay, so for this one, we have a polynomial of degree 5. Okay, so 0, 1, 2, 3, 4, 5. So we are the generating function associated with this sequence is this polynomial, and you can see that it is 1 plus x to the power 5. So we do, for formal power series, we can do all the usual algebraic operation as if we do with polynomials and normal power series. Okay. So what does it mean? It means that we will try to define the operations sum and product. Okay. For the sum, it is simple. You know that when you sum two power series, the result is also a power series, and we group the terms of the same degrees. And if f is the generating function of the sequence an, and g is the generating function of the sequence bn, then the sum of f and g is the generating function of the sum of the total sequence. Okay, so you can write it to verify. I think that this is quite obvious, right? So there's maybe no need to another simple operation is the product by a scalar. Okay, if you scale up, if you multiply a generating function by a scalar lambda, by scalar I mean just a number. Okay, then you obtain the generating function of the corresponding sequence. Okay, you multiply every term of the sequence with the same scalar. Okay, so these two operations are straightforward. Okay, so we notice that means, what does it mean? That means that the sum of two formal power series is also a formal power series, because it can be written in this form. And the product of a formal power series with a scalar is also a formal power series, and the result is given by these formulas. Okay, and now we do something a little more complicated. Okay, so the product of, here we have seen the product of a formal power series with a number, and here we will see that the product of two formal power series is also a formal power series. But the term here, even if the notation is a little complicated with a lot of indices here, it is in fact simple. It is the same as when you multiply two polynomials, except that here, instead of polynomials, you have infinite sums. But the principle is the same. If you want to, so first we state that the product of two formal power series is also a formal power series. Okay, and the coefficients in detail, in particular the coefficients of the product series is given by this. So suppose that let us see how we obtain that. Now suppose that f times g is equal to a power series h with coefficients, let's say Cn. Okay, n goes from 0 to infinity, and we write f as the sum of an x to the power n and g as the sum of bn x to the power n. Okay? And in fact, when we multiply two power series, we do, since they are the sum, we use the distribution law. Okay? We multiply each term of the first sum with each and every term of the second sum. Okay, so if you write it as a0 plus a1x plus a2x squared plus etc. And here is b0 plus b1x plus b2x squared and so on. Then in fact you will get a0 b0 plus here you get a0 b1 x a0 b2 x squared and so on. Okay, so for the second it's the same, but we will for convenience we will align the terms by the degree of x. So we will write a1 b0 x plus a1 b1 x squared plus a1 b2 x cubic, so on. Okay, so here you will get similarly a2 b0 x squared and etc. And then you notice that if you write if you develop the product like this one, then and you sum by the column, then you get, for the coefficient of x here is a0 b1 plus a1 b0. Okay, so here the coefficient of x squared will be this, because from the next line and lower there will be no term with no term corresponding to x squared and so on. And here if we so if you do this for for every power of x, then you get this. In fact, it is a sum if you replace n with 0 here, then you get a0, b0, okay? So for example, if n is equal to 2 here, you get a0, b2 plus a1, b1 plus a2, b0, and so on, okay? And the next operation is maybe new for you, okay? So if calculus you haven't seen series, then this is new. Have you seen Taylor series, Taylor development in calculus? Huh? Yeah. So this is the same as power series in calculus, okay? But in so there are more nuance, but in the context of our courses, we work only with nice power series. That is, we don't need to prove, but we admit that for the power series in our course, we can do this. Okay. So this, in fact, there are some conditions, but we admit this. Okay. So if f is the generating function for the sequence an here, then we can take the derivative of f, okay? And you can see that it is the same. You take the derivative of f, then you obtain the sum, where each term is the derivative of the corresponding term. For example, here, the general term here is an x to the power n. If you take the derivative here, you will get n will move here, okay? An stays the same, and the power of x will be reduced by 1, so you get this term. And of course, if n is equal to 1, you have a constant term here, so when you take the derivative, the constant term will become 0, so you move the index one step here. You ignore the. And for convenience, if you want that your series is indexed by n, then you will do an index shift here. Okay, so here we do a change of index. Instead of n, if we want to change n minus 1 to n here, then here instead of n we need n plus 1, and here instead of n we need n plus 1, and this time if n goes from 1 to infinity, then n minus 1 goes from 0 to infinity. Okay, so this is simply a changing of index. So to summarize, for formal power series, you can do these basic operations. Okay, you can do the sum, you can multiply by a scalar, or you can multiply two power series, or you can take the derivative. And of course, you can do the converse of the derivative. You can also take the primitive. Okay, you can also take the primitive of a power series. Okay, so let us illustrate these operations with an example. So we go back to the Maclaurin series. Okay, so that was the series corresponding to the O1 sequence, the sequence where every term is equal to 1. So you have 1 plus x squared and so on. Okay, and here we admit that we can simplify this like we do in calculus. That is, this sum is simplified to 1 over 1 minus x. Okay? So we will try to do some operations, apply operations on this power series. So if we take the derivative of this, okay? So according to our previous slide, we will. It's the same as we are as taking the derivative of each term. So here we we get the left hand side will become the sum of n plus 1 times x to the power n, where n goes from 0 to infinity, okay, is g prime here. And since g is equal to 1 over n 1 minus x, we can also take the derivative of the right hand side here, and we obtain this. Okay? So from this identity of about the Maclaurin series here, we get another identity. Okay, so from this we find that this series in fact can be reduced to 1 over 1 minus x squared. Okay, so if you write it in detail, instead of using the sigma notation, then you will that means that the sum on the left hand side is if n is 0, then it's 1 plus 2x plus 3x squared, okay, plus 4 is and so on will be equal to 1 over 1 minus x squared. Or if you want to write it in another form, you have 1 minus x to the power minus 2. Okay? So you can verify that it is the same if you do the reverse. You use the Taylor series expansion of this function, and you can find a similar result. Okay, so it's the same. It's the same, except that here we admit we don't verify any conversions or any analysis property of the series. So the power series here for us, it's simply symbolic. It is formal. Okay? Of course, you can find this result in another way. Here, you can remark that this right-hand side can be written as gx g squared. Okay. So instead of taking the derivative, we can do it another way. We can calculate the product of g with itself. So we write the two power series like this, and we use the formula for the product here. But here it is rather simple because every ai and bi are 1. So in fact, this sum here is simply equal to the number of terms, because every term is equal to 1. Okay? So here we simply count the number of terms, and we know that. So here, since it is a sum where the index goes from 0 to n, we know that there are n plus 1 terms in this, and each term is equal to 1, so we get n plus 1. Okay? So you have some identities like this, and sometimes each identity can be found by more than one way. Okay, so you can take the derivative, or you can take the product. I don't know if you can find it another. So you will see that there's another way to do that if we apply the general Newton binomial formula that we will see later. Okay, so now, in fact, I talked about another way. Because if you write the right hand side as 1 minus x to the power minus 2, and you somehow can extend the binomial formula for negative exponents, then you can hope that you can find another formula for that. So here we will see how we can extend the binomial formula for general exponents. Okay, so in binomial formula we have binomial coefficients. So in order to to find general binomial formulas or extended binomial formula, we need to first define the extended binomial coefficient. Okay? So here we know that in our standard, in the normal classical binomial formula, the binomial coefficient is n choose k. Okay? N is the exponent. Okay? So in order to define the formula for the arbitrary exponent, not necessarily integer, we need to define this quantity alpha choose k, where alpha may not be positive integer. Okay? So here, so this is the formula. So the idea is that, so you can see that if you let alpha be some positive integer greater than k, then you find the normal formula for binomial coefficients. Okay. So here we know that n choose k is equal to n factorial divided by k factorial n minus k factorial. Okay. But we can also simplify this. If we simplify, you know that this factor n minus k factorial is present in this product. So if we simplify every term here from 1 to n minus k, we are left with n times n minus 1 etc. times n minus k plus 1 divided by k factorial. Okay? So that's where the idea comes from. So if we write our normal coefficient, binomial coefficient this way, and we will replace n with an arbitrary real number alpha instead of integer, then we obtain this formula for extended binomial coefficient. Okay? So you write the same formula for normal binomial coefficient, except that you replace n, the integer n, with an arbitrary real number alpha. Okay, so we distinguish two cases where k is strictly positive and where k is 0. So as usual, if k is 0, we define the coefficient to be 1. Okay, for convenience, for consistencies in calculation. Okay. And if k is different from 0, then we get this. So you can see that this way you can define the binomial coefficient for example, first negative integer, or for fractions, or even for real number. Okay. So some special cases. Okay. So for if alpha is a negative integer, that is to say if alpha is minus n, where n is a positive integer, then we get this formula. Okay, so note these cases because maybe you will use these cases. Will be used quite frequently. So it will be useful if you note them down somewhere easy to find. Okay. So in fact, let's see. So for negative integer n, if we apply the formula, then we get minus n. Okay, so here minus n choose k. If we apply the formula, we have alpha here is minus n, okay, times minus n minus 1, and so on, times minus n minus k plus 1, divided by k factorial for k positive integer. Okay. So here, as usual, for convenience, we will get rid of every minus. So we put there are k terms, k factors, so we get minus 1 to the power k, and we will have n plus 1, and so on to n plus k minus 1, divided by k factorial. Okay? But now, once again, it looks quite familiar. Okay? So you have a factorial below in the denominator, and you have a product of k consecutive positive integer in the numerator. So this is once again binomial coefficients, but instead of n choose k, you know that it is the largest term here. If you can write this as times n factorial. N. If you add the missing factors to make it a factorial, then you need to multiply the thing below with n minus 1. Okay, n minus 1 factorial, and this is exactly this. Okay, so you find this. So even if the proof or the proof to derive this is not given on the slide, it is simple enough, and it is recommended that you verify this yourself. It is not difficult. It is a simple exercise of applying the formula above with a particular case. Okay, so do some calculations, okay, and verify that it is true. And in the next, for non-integer alpha, it is a little more complicated, but I give this case because it will be useful. It will be used later for Catalan numbers. Okay, so now this formula will require some more involved calculation, but not much more complicated, except that here we need to some power of 2. So there will be two or 3 additional steps, but the principle is the same. You replace alpha with 1/2 here in this formula, and instead of this nice product of consecutive integers, you will need some. You will have some product of consecutive odd integers. So I will do it here for you. Okay. So why do we do that for 1/2? Because with what will correspond to the power 1/2 is the square root. Okay, if we want to be able to do to work with generating functions of where the square root is involved, we need to calculate something like this. Okay, so now we have 1/2 choose k. Okay, we will apply that formula. Okay, so first we have a factor of 1 over k factorial. Okay, and above, what do we have? We have 1/2. Okay, times 1/2 minus 1. 1/2 minus 2, and so on. And what is the last term? Is 1/2 minus k plus 1. Okay? So, in order to not make mistake, we will write everything very, very carefully detailed here, and we do the calculation steps slowly but surely. Okay, so here you have 1/2. Okay, so the second term is minus 1/2, and then you have minus 3/2. And if you carry on, you will have minus 5/2. Okay, so each time you decrease by 1. So, and finally, what is this? It will be minus 2k plus 3/2. Okay, if we put the minus sign here, you get this. Okay, so we do it step by step. We keep the 1/k factorial here, and now the next step we will want to get rid of all the minus sign. How many minuses are there? So you have 1, 2. So you have to count the number of odd numbers from 1 to 2k minus 3. So this one is 1. You can write it as 1 times 1 minus 1, and here it is 2 times k minus 1 minus 1. So you have something like minus 1 to the power k minus 1. Okay? And then how many 2's are there? We have this many, but with an additional 2 here, so you have 1/2 to the power k. Okay? And then you have the product of all the odd numbers from 1 to 2k minus 3. Now you need some algebraic skill to go from this to this. How? So the goal is that we want to, in order to get to this, you need some factorial. Okay, so factorial terms. But the problem is that here we don't have the term of product of consecutive integers. We only have odd numbers here. So if we want to make it a product of consecutive integers, we need to add even numbers. Okay? So this we can write it as, so this will carry on over here, and this will become, if I insert the even numbers, then I have, so I need to insert 2 here, 4 here, and 2k minus 2 here, so I get 2k minus 2 factorial divided by 2 times 4 times 6 times and so on times 2k minus 2. Okay? But here the nice thing with even numbers is that you can move the factors 2 outside and you obtain inside a factorial. Okay? So here how many 2's can you put outside? Here we have another 2. So this will stay here. So I will replace this bit here. And you get 1 over k factorial times minus 1 to the power k minus 1 divided by 2 to the power k. Okay? And here we have 2k minus 2 factorial divided by, if we put 2 outside, then we have 2 to the power k minus 1. Okay, and inside we have k minus 1 factorial. Okay, so now we are almost there. We have a factorial here, k minus 1 factorial here, so in order to make it a binomial coefficient, there is k minus 1 factorial missing. Okay? But here k minus 1 factorial is in here. Okay, so we can write this as k times k minus 1 factorial. So it will become, if we rearrange the terms, then you have a term corresponding to the sign here. Okay? So here we have k left times 2 to the power 2k minus 1, and here we have 2k minus 2 factorial divided by k minus 1 factorial k minus 1 factorial. Okay? And now you can see that this is exactly here, so here you can write this as 2 here, and if you put 2 outside, then you get 4 to the power k minus 1. Okay, so I leave the rest to you to go from this expression to the expression on the right hand side here. Okay? So in order to really understand it, you should try to prove these kind of formulas. Okay? If you only look at it like this, then you will never be able to use them in exercises. So everything comes with practices. Without practicing, you will never be good anything. Okay. So now once we have defined this extended binomial coefficient, we are ready to state our extended binomial formula. Okay, so here, first notice that we don't state the extended binomial formula for a plus b, but here in this formula we always have the form 1 plus x. Okay. So of course, if you want to have a plus b, you can also always put a factor outside. You can always write you can always write a plus b to the power of something as if a is different from 0, then you can write it as a plus alpha times 1 plus a over b to the power alpha. Okay? But now for generating functions, we will use this form. Okay? So you can see that it's the same as the normal binomial formula. That means that if you want to have a trick to remember this, then first try to write this formula for positive integer alpha. Okay, and then you replace alpha with some generic value, and you replace the finite sum with an infinite sum. Okay? Okay, so we go back to our example on McLaurin series. Okay, so as I said, we can write the term g squared as 1 minus x to the power minus 2 here. Okay, and then if we apply this formula, then we get this. And on the previous slide, fortunately, luckily, we had already calculated this. So we can replace 2 here. If n is 2 here, then we have, if n is equal to 2, then here, inside here is actually k plus 1 choose k, okay? Which is equal to k plus 1, by the way. So here you have, in fact, minus 2 choose n, minus 2 choose n, according to the previous slide, is equal to minus 1 to the power n, right, times minus 2, what was it? So 2 plus n minus 1 choose n. Okay? So here, since you have minus x to the power n, the minus of the x and the minus of this factor will cancel out each other, and you have no minus sign left. So everything becomes positive. And this one is actually n plus 1 choose n. You know that it is n plus 1. So you get this formula. So in these examples, you have seen that you can derive the same formula in three ways. Okay, so you can either take the derivative, you can calculate the product, or you can use this extended binomial formula. Okay, so now the second example will show you an application of this thing that we have tried to derive. Okay. So here for square root of 1 plus x. Okay, so if you apply the normally the Taylor series expansion, then it may be the calculations may become complicated very quickly. But if we have already known this formula, then we can apply mechanically this formula with alpha equal to 1/2 here, and you get this. Okay, so once again, luckily we have already prepared the calculation of this extended binomial coefficient. So we replace, you plug this formula into this equation here, and you get this expression. Okay. So here I give you the final result, but it is your job to convince ourselves of the result. Okay. Use the formula on the previous slide and do some calculations and verify that it is exactly this. And once you have done this, you can try another further step by trying to find this expression from this yourself. Okay. Okay, so on this slide, you are given some useful power series. Okay, so this looks familiar. You might have seen this in calculus, but here it is. So you can use these to calculate generating functions. Okay, you can print out this slide to keep as like a cheat sheet. Okay, so here, in fact, the first four identities are actually the the same extended binomial formula, but applied to special cases. Okay, so this one, the first one, is the extended binomial formula applied for the case where the exponent alpha is positive integer. Okay? The second one is a modification of the Maclaurin series, but instead of x, you have the term ax, where a is a constant factor here. Here is also the Maclaurin series, but applied with x to the power k instead of x. So you can see that the form is very similar to Maclaurin series. So this is also similar. Okay, this one is the extended binomial formula. So this one is similar to the first one, except that you have a minus x here, but so you do some different calculations. And there is also a minus term in the exponent. So this is 1 minus x to the power minus k. Okay? So in fact, this one you can also find this one by taking successive derivatives from the Maclaurin series. The next one, this one, you can see that this is the definition of the exponential function. Okay, so it applies directly here. The last one can be maybe consider the converse of the exponential function. Okay, so you have something with the exponential here and something with the log. So you have polynomial, you have fractions, you have exponential, you have log. So those are the basic functions. So now, I guess with this list, you are equipped with necessary tools to do the exercises and to do the calculations in the scope of this course. Okay, so let us take a break before looking at the applications of generative functions.
tuần. Cái video
Hả? Nghe xong rồi. Bây giờ tôi làm cái này là
3 giờ. Mình sẽ sai không hiểu đâu. Sai nó thành mạnh kiểu không phải cái đâu hiểu mà cái này tao hiểu thật, cái này bê đưa không phải ai bê để nào là cái gì không có cái tao nhìn cái không có mày chỉ cần nhớ cái so sao nãy mua mấy cục xích con
Mình bán xem.
nó 20 triệu.
Đúng. Tao mua hai cái bánh mì. Và tao mua thì tao mua.
20 nghìn đấy, 20 nghìn rẻ à?
Hả?
Mua gói ngoài 30.
Nói chung vẫn đắt. Thà tôi mua mày hai cái bánh mì.
Còn 40 nghìn thì chúng ta sẽ ăn được xích con. Cái đấy là gói 5 cái.
4.
1 cái ạ. Cái 5 nghìn cái. Bán lẻ là bán 7
Okay. So let us see how we can apply generating functions to solve counting problems. Okay, so in the first example, we look at a simple problem. Suppose that we have three types of notes: $1, $2, and $5. The question is that how many ways you can make a sum of $7 using these values. Okay, assuming that the order is not important. So you can list all the possibilities. Of course, that is a way to do it, but that way is not quite feasible for large sum of money. Okay, so you can easily do it for $7, but let's say for $70, that would be more complicated. Of course, for those in computer science, you know that there are intelligent ways to address these problems, algorithms. Okay, but now if we want to use generating functions, then how can we do it? Okay. So now the way we look at this is that we want to make a sum of $7. Okay. So in this sum of $7, we have three types of notes: $1, $2, and $5. So basically, we will look at the number of ways to combine the three types of sum into one larger type of sum. So if we use only $1 notes, then what are the values can we make? So we can have $0, of course, or 1, or 2, or 3, and so on. All the integer values. Okay. So if we consider this sequence of values, a sequence of numbers, then we can associate this with a generating function. Okay? So this will become 1 plus. So you have 0 here. Okay? So this is with 0 note of $1. Okay? So this is 1, this is 2, this is 3. So you have, so this is 1 note, so we have x, okay? So this is, there is one way to make this, so you have x squared and x cubed and so on. And similarly, if we use only $2 notes, then we can make 0, 2, 4, and 6, and so on. Okay, so we have one way to make $0. So it corresponds to x to the power 0. So here x to the power 1, here x to the power 2. So it will become x squared plus x to the power 4 plus x to the power 6. Okay? The reason here is that, so it is quite not intuitive to explain. How do we explain this? If we use only notes of $5, then we have 0, 5, 10, 15, and so on. And so we have 1 plus x5 plus x to the power 10 plus x to the power 15. In fact, here we are counting the number of ways. So we keep the series like that, and let me explain it in another way. Okay. So if we have values in dollars, okay. And we have using the nodes here. We take a look at all the possible values of the sums in dollars. So 0, 1, 2, 3, 4, 5. Okay. So if we use so this will denote the number of ways with the $1 notes. Okay. So in order to make $0, there is one way. Okay. You can use 0 notes. Number of way 1. Okay. So if you want to make a sum of $1 using only this note, then there is only one way. Okay. To make this sum of 2, there is only one way. Yeah, two notes. Okay, because here the order of the notes doesn't matter, so there's only one way. Okay, and so on. So that explains the coefficients here. Okay, so that means that this will correspond to x to the power 0. X to the power 1, x to the power 2, x to the power 3, x to the power 4, x to the power 5, and so on. Okay? So the values here correspond to the terms, the powers of x in our power series, and the number of ways are the coefficients. So if we do the same, if we look at the number of ways to make that sum with $2 notes only, okay? So in order to make $0, we have one way with 0 notes, okay? In order to make $1, so it is impossible if you have $2. If you only have $2, you cannot make $1. Okay? So there's 0 way here. But for $2, you have one way. So here, for the odd numbers, you cannot make these odd numbers with only $2 note. So So here, so here the coefficients here correspond to the number of ways to make the corresponding sum with those nodes. So you have alternatively 1 and 0. So that explains this power series here. You can see that the coefficient of x0 is 1. So there is no term corresponding to x here. So in fact, the coefficient of degree 1 is 0. So if you multiply this, you take the sum, then you get this. So you can see that it is the same with the $5 notes. Okay, so here you have one way to make $0. You have one way to make $5. And all the other values, you cannot make those values with only $5 notes. So you have 0 elsewhere. So here you have in your sum all the terms corresponding to exponents not divisible by 5 are 0. Okay? And for the multiples of 5, you have only one way, so all the coefficients are 1. So here it is written on the slide, but it is not. It is quite complex. So if you want to understand it more, you should write. You should create this table, and you understand that the total values correspond to the exponents of the terms here, and the number of ways to create that value correspond to the coefficients. So here, since we don't care about the order, so for each type of node, if you can either make that sum or not. So if you can make that sum, you have 1 here. If you cannot, you have 0, and you combine it, you get the series given there. And now, if we take the products of those 3 generating functions, then we get the generating functions which will give us the number of ways to make a certain sum. Why? For example, here, if we look at the value so here, if for example, for the value of $5, okay, we can, if we take $2 of this type, sorry, if we can take $3 of the $1 notes, and $2 of this type, and $0 of this type, then you have one way. And this way corresponds to what? This way corresponds to x to the power 3 times x squared times x0. So that corresponds to the x group here times this and times this term. So you basically, maybe if you understand it's good, but if you don't see the inside, then it is sufficient to remember that this product will give you, if you calculate this product according to our result, you know that the result is also a formal power series, is a generating function. And that generating function will give you the number of ways to make a certain amount of dollars. Okay, so if we calculate this, so the question is, how many ways to make $7? If we want to look at the number of ways to make $7, so we need to find the coefficient of x power 7 in this generating function. Okay? So if in fact these series are infinite, But if we are interested in only x to the power 7, we can cut off these sums. We can cut off at the powers smaller than or equal to 7. And if you do the calculation, you will find that the coefficient of x to the power 7 here is 6. Okay, so I will do it once more in detail for you. But, this is supposed to be a simple algebraic problem. You should be able to do it yourself. Okay, so we have 1 plus x. I will write for each sub-series here all the terms corresponding to a sum smaller than or equal to 7. Okay? And here I will have 1, x, 2, 4, and 6. So from x to the power 8, I can ignore because x to the power 8 multiplied by something here and something after will give you a power larger than 7. So here we are interested in only the terms corresponding to power smaller than or equal to 7. Okay? So now you can truncate these sums at these cutoff values here, and you do the normal calculation and find what is the power of 7 in here. So in fact here you can start with this. If you start with 1 here, then you can go from larger to smaller, and you can find this will be equal to 1 plus x plus something plus and to 6x to the power 7. Okay? So that means that each time you have a sum made of $1 here and a sum made of $2 here and a sum made of $5 here. If you multiply and you see that the total exponent is 7, that means that it gives you a way to make $7. Okay, so if we look at the coefficient here, it gives us a number of way. And of course, in computer science, once you know the dynamic programming, then you can easily solve this type of problems. Okay, so the second example looks familiar, but this one is one that we haven't treated before. Okay, so we have seen that we can use formulas of permutations and combinations to find the number of integer solutions to this type of equation. But here, we know how to answer these questions for general case, okay, or for cases with low bounds. But here we consider the same or similar the same type of equation, but with a more complicated set of constraints. Okay, so here not only lower bound, we have upper bounds. And in fact, here we demand that x1 must only take values from 2 to 4. x2 similarly must only take values from 3 to 5. And x3, even more complicated, we demand that x3 is a number divisible by 3. That is 0, 3, 6, 9, and so on. Okay? So if you list all the possibilities, it will quickly become a mess. But here, once we have the powerful tool, which is generating function, this becomes a simple algebraic program. First, we write the generating function corresponding to each variable. Okay? So now, because of these constraints, x1 can only take the values 2, 3, or 4. Okay? So the corresponding generating function for x1 has only the terms of powers 2, 3, and 4, and all the other terms are 0. And similarly, the generating function for x2 is x to the power 3 plus x to the power 4 plus x to the power 5. Okay? And here, since x3 must be divisible by 3, we keep only the terms with an exponent 0, 3, 6, 9, and so on. And now once again we calculate so now our generating function has this form here. And it remains to calculate the product to find the coefficient of x10 in this product. So here you can put x squared and x cubed outside as common factor, and when you do the calculation, it will be simpler. Okay. So after some exercise, calculating some calculations, you find that the coefficient of x to the power 10 in this expression is 10. Okay. So of course here, this is an infinite sum, but since we are interested in only x to the power 10, you can cut off here, because the next term is x to the power 12. Okay? So if we are interested in a certain term, then we can cut off every term with which comes after it. Okay, so do you understand the technique to answer this kind of questions? You have an equation like this. You have a set of constraints, conditions here. You use these conditions to write the generating functions for each variable. Okay? So here, note that in the generating functions, only the exponents corresponding to possible values of each variable here are present. Okay? So here x1 can only be can only be 2, 3, or 4. So you keep only terms corresponding to the exponent 2, 3, or 4 here, and all the other exponents you set to 0. Okay? So here is the same. x3 can be 3, 4, or 5. So here you have only 3 terms, x to the power 3, 4, or 5. Okay? For x3, the only possible exponents are the ones divisible by 3. So you keep only 0, 3, 6, 9, 12, and so on. And you get this? Okay? And since here you have 10 on the right hand side, you will look for x to the power, the coefficient of x to the power 10 in the result. Okay? Now we revisit a familiar counting problem. So you know already, I hope, how to solve this using the formulas for arrangements. Okay. So now if we look at so here I introduce another way to use generating functions to solve this counting problem. Okay. So here the setup is we have n identical balls we have k different boxes, and we want to distribute these balls into the boxes so that none of the boxes is empty. So now, how can you use generating function to solve this? So, in fact, you can rewrite this problem as follows. You can, if you still haven't forgotten how we did it, you see that we can bring this problem to a form similar to this. Okay. So how many variables are there? So in fact, here it is an equation of k variables. Okay. So if you call the number of balls in box number 1 is 1, and so on, then you need that the total number of balls in the k boxes is equal to n. Okay? And what are the conditions? You want that, so here xi integers, okay? And since you want that all the boxes are non-empty, xi must be greater than or equal to 1. Okay, so you know how to solve this using the formula that we have seen. I don't remember in the second or third lecture. Okay, but now we can write the generating function for the number of balls in each box. And in fact, for each box, the generating function for the number of balls is the same. Okay, so you know that the number of balls in each box can be any positive integer. Okay, so here, in fact, you can truncate this sum because it will be bounded above by n, but we don't care about that. Okay, so since it cannot be 0, we start with exponent 1, so we have this sum. And we write the generating function for the total number of balls in the boxes. Okay, we get this. So each box have this, and we have k boxes, so we have this product. Now, can we use what we have already seen to simplify this generating function? Okay. What tools do we have? So the first thing is that you put x outside. Okay. So for all the generating functions that we have, all the formal power series that we have already seen, the starting coefficient is 1. So now we put we see that there is a common factor x in each sum. So we can write g as x to the power k. Then inside you have 1 plus x squared plus so on to the power k. Okay? So now this looks familiar. It's the Maclaurin series. And you can write it as x to the power k. So this one is 1 minus x to the power minus 1 n to the power k, and it becomes x to the power k 1 minus x to the power minus k. Okay? So now we don't have to redo the calculation because we already have our cheat sheet here. So this corresponds to this, I guess. So it's this one, okay? So this is 1 minus x to the power minus k. So So we have this one. So we will write. So we have. So G is equal to x to the power k times that's the sum of n plus k minus 1 choose n, x to the power n, where n goes from 0 to infinity. Okay, so this is our generating function. Okay, so why do we have this? So in fact here I should have we should not use n here because it's redundant. So let's say we use another I, okay? I here. Okay. So now this is our generating function, and we want the total number of poles is n. So if we want to find the x to the power n in this function, then what is I? What value of I should we choose? So we should look at I equal to n minus k, okay? Because if we
Cái VS Code của ông Hưng là chạy
I here x to the power I. So if we remove if we put k inside, then we have I plus k here. So this is our function. So if we want that I plus k is equal to n, then the corresponding coefficient is also I. Okay. So that means that I is equal to n minus k, and we plug it in here. With I equal to n minus k, we get n minus 1, choose n minus k, which is this number. Okay? So you can see that in combinatorics, you have the same problem. You can have many ways to solve this problem. Okay, so another important application of generating functions is that you can use generating function to solve recurrence relation. And now I will show you an example how to use the generating function how to calculate the generating function for the Fibonacci sequence. And from that we can find the formula for the general term of the sequence. Okay. So let us remind ourselves that the Fibonacci sequence is defined by this recurrence relation with these initial conditions. Okay? So here pay attention, because generating functions are powerful to solve recurrence relation, but this approach will require quite careful calculations. Okay, so you should be good with algebraic manipulation to solve. Okay, so we write the general the generating function for this sequence. Okay, is it 10 or do we finish at minus 10 or? So it's time that we can leave this for next week. Okay. Next week we will talk about this. And for now, try to redo the example. Okay? Try to redo the examples about all the formulas. Try to derive the formula yourself to understand. We will continue next week.
Tôi có học, tôi học ở lớp khác. Tôi học cùng bọn, tôi học chung với A Bùn, học trước. Bây tôi không về, nhà tôi xa ấy.
Ông này B mấy nhỉ?
B1, B. Tôi nhà tôi xa thì tôi về sau.
Bao nhiêu cây?
Ở Hà Đông.
Vậy. Em như là bao nhiêu cây?
11 cây.
Ok, đây thì cũng hơn tôi được 1 cây chứ mấy.